Welcome to the Mizzou Cloud and DevOps curriculum series for online learning. My name is Songji Wang. I am a cyber infrastructure engineer at the University of Missouri. In this video, I'm going to show you the third lab in our learning series, the KubeEdge for edge computing with bioinformatics application. The purpose of this lab is to show you how to set up a KubeEdge cluster and manage edge computing capabilities on the public cloud, Amazon AWS. The topic of this lab include the technology that we're going to use is mainly the KubeEdge cluster with edge computing capability. And the platform in this case we will use Amazon AWS cloud platform, and on the platform we will create several simple AWS EC2 instances to run the KubeEdge cluster and our use case applications. So the use case application will be the volunteer edge computing with the bioinformatics workflows through a multi-cloud resource broker called on-time URB. First, I'll briefly introduce KubeEdge. So KubeEdge is an open source platform that enables edge computing within a Kubernetes cluster. So with this KubeEdge system, you can create host machines not only in the cloud, but also on the edge side, which could be either a laptop or some IoT devices attached to your machine. So the KubeEdge is built on top of Kubernetes, and it provides fundamental infrastructure support in terms of networking, application deployment, and message synchronization between the cloud and edge hosts. So you can see from the image below here, the KubeEdge include most of the main components in a Kubernetes cluster, as well as the API server. So through a kubecontrol commands, you can run, you can talk to the API server and issue command to the edge devices. So the command will go to the device controller, and then the device controller on the cloud hand side will communicate to the edge side, the device twin, through hubs, which include the cloud hub and the edge hub. Based on this communication, the commands can be issued to the edge nodes, and based on the events stored in the message, the Mosquito message queue will use a mapper to map the application or jobs to an edge node device. In this case, you bring up a Kubernetes cluster not only in the cloud, but also on your edge side with your local machine or IoT devices. In this lab, we will use a research-based application named Volunteer Edge Computing for Bioinformatics. So this application enables researchers to define the minimal resources that they require for running their HPC jobs in the cloud. So based on the definition, the on-time URB will automatically pick the best cloud platform to run the HPC jobs based on the resource required for the job and the associated costs, security. So it's multi-parameter consideration. So based on this consideration, the on-time URB will allocate the best public cloud platform to run the HPC job for the user. Through the on-time URB, we will be able to reduce the time that the user needs to spend on running their jobs, as well as minimize the cost that comes with using the public clouds. The on-time URB leverage several frameworks and tools to make everything happen. These include Pegasus workflow management system, an HT Condor scheduler, and PyGlide-in Python client to be able to send the job to a client nodes in a computing cluster. So in the figure down below, you can see that the Pegasus system has a planner and a scheduler engine. So the planner will help the user to define a HPC job in terms of DAG file, and then the HT Condor scheduler in this case will be able to submit the job after the user define the workflows. So the HT Condor will be connected to the computing resource on the HPC side and decide which one or which nodes to run the HPC jobs. In this lab, we will guide the students to deploy a KubeEdge cluster on AWS Cloud with several AWS EC2 instances. And we will manage the cluster to include both Cloud Core and multiple Edge Core nodes within the public cloud platform. And these different nodes will have different computing resource configurations to show you the differences in terms of performance in the cloud. On these cloud and edge core nodes, we will deploy Docker-based containers with trusted bioinformatics workflows that we have created based on our research projects to be able to run on HPC jobs within the cluster. Under the hood, our application will use volunteer edge computing algorithms that we created to automatically select edge nodes to maximize the performance while lowering the cost to run these jobs in the cloud. To be able to access the lab instruction for this lab, you will need to go to this website and log into our web application. As a prerequisites for this lab, first you will need to have a GitHub account. So you will use this GitHub account to log into our web portal. So the prerequisites for this lab, the first one is you need to have a GitHub account. If you have done our previous labs in the learning series, then you should be able to log into the web portal without problem. But if it's the first time that you're trying to execute this lab, or if you have never used the GitHub, then you need to create an account on GitHub to be able to access our learning module. Once you have your GitHub account ready, you can click the link below to log into our Mizzou Cloud and DevOps web portal. Once you log in there, you need to request for an approval from our admin. So if it's the first time that you can log into this portal, you will need to submit a form to our system admin. Once you are approved, you will be able to log back into the portal and register for a lab module and access the lab instruction for this lab. Once you have access to the lab instruction, you will also need to have an AWS account to run this lab. Again, if you don't have one, please register for an account to execute this lab. So the lab steps are as follows. First, we provide some overview and getting started with the KubeEdge with some basic information as well as some links that you can click and then learn the relative information about this system. After you are familiar with the KubeEdge, you can go ahead and execute the main tasks of this lab. So we organize the contents into 3 main tasks. The first one is the KubeEdge cluster installation and configuration. So in this task, you will bring up several AWS EC2 instances and install KubeEdge cluster on it. Once you configure the KubeEdge cluster, you will go to the second task, the KubeEdge counter demo application, and in this task, you will download and install one of KubeEdge's counter application with a controller in the cloud node and the counter application running on the edge node. So in the third task, we will introduce to you our research-based use case application, edge computing with bioinformatics. So in this task, we will show you how to run our volunteer edge computing with bioinformatics application in the KubeEdge cluster. So once you're done with all these 3 tasks, please clean up your lab resources or the AWS EC2 instances in your account so you don't get charged after this lab. In this video, I'm going to go through all these 3 different tasks and then just show you how everything works so you can repeat these tasks on your own. Task 1, KubeEdge cluster installation and configuration. For this lab, we're going to create our KubeEdge cluster using Amazon AWS EC2 services. From the AWS EC2 services page, the first step is to create a key pair, which you can use to log on to the instances. If you click Create Key Pair, you can see you can configure the key pair with the encryption type. In this case, we're using RSA encryption, and the file format for this key will be a .pam file. You can input an appropriate name for this key pair and hit Create Key Pair. If you already have one in your account, you can skip this step and use the one that you already have to log into your AWS EC2 instances. After you create your key pair, go to the security groups to configure the security group with the inbound and outbound policies to connect to your instances. In the inbound rules, it's essential to have the last one that I'm showing here to configure the all TCP connection within the port range from 0 to 65535 to allow communications between the EC2 instances in the cluster as well as connecting to the web services. After you create your security groups, click the instances on the left of your page and then launch instances on the top right corner to create your first AWS instance for the cluster. In this lab, we're going to create 3 nodes. Each one will be running a Ubuntu Server 20.04 as our operating system. So in this video, we're going to show you just how to create the first one, and then you can continue with the other 2. So for the first instance, we're going to use it for our Cloud Core node in the cluster. In this case, we're going to pick the T2.medium machine type. And in the configure instance, leave everything as default and then change the storage from 8 to 30 gigabytes for this instance. In the next step, add text. You can choose to add some text to your instance by adding a key pair value or leave it as blank. In the configure security group, you will select an existing security group with the one you just created in the previous step. So this security group will have the configuration for the inbound policies that you can connect to your instance. Click Review and Launch. In the review page, you will look at the information that you just input for the instance, and if everything is correct, just hit Launch. You will then be popped up with a box asking for an existing key pair. In this case, you will select a key pair that you just created in the previous step. Click Launch Instances, then your AWS EC2 instance will be created and will be ready for you to use in about a minute. Click View Instances, you will be redirected back to the main EC2 service page where you can look at the status of your EC2 instance, as well as create your next instance by clicking the Launch Instances again. From now on, you will create the next 2 instances in the cluster. Both are worker nodes, and then one is a T2.micro instance type, while the other one is T2.large instance type. So from now on, we're going to fast forward our video just to skip all the steps that you have done previously, and then we'll come back later. Once you have created all the three AWS EC2 instances, we'll switch to the terminal, and then you can log in to those instances using the key pairs that you created in the previous step. Once you log into the AWS EC2 instance, we'll show you how to set up the KubeEdge cluster on each of the nodes. From the master node, first, run sudo su command to change to the root mode, and then go to the /root directory. From the root directory, run git clone command to clone our GitHub repository that we prepared for this lab. After you clone the Git repository, run the two seed commands that we're showing here in the screen to configure the SSH remote login. With this SSH remote login, the nodes within the KubeEdge cluster can talk to each other, log into each other, and send and receive files. After you configure the SSH remote login, restart SSH daemon, and then reset the password of the user on this machine. Once you're done with the configuration here, go back to the /root directory and run the installation command that we specify in the GitHub repository. So the command will be bash, the path of the installation file, and then the name of the shell file is cloudcore install.sh, followed by the IP of the AWS EC2 instance from your account. The KubeEdge installation on each of the nodes will take quite some time. While we were waiting for the CloudCore node to install everything, we can switch to each of the worker node to run the same commands as we did on the CloudCore node. After you configure the worker node in the cluster, the only difference will be the installation command, as we're showing here. On each of the edge core node, you will be running a bash, the path of the installation file, and edge core install.shell to install the KubeEdge on the worker node in the cluster. If you see a pop-up screen on any of your nodes asking you to configure the OpenSSH server, this is because you modified the SSH configuration and it's asking you to verify. Just select the second one to keep the local version that you just installed and continue. After a while, you can see from the left of your screen showing that after a bunch of library and tools installation, the KubeEdge has been installed correctly on the master node. The next step on the cloud node will be obtain the token that the worker node will be using to join to the cluster that has been created on the CloudCore node. You need to copy this token string and use it when you're running on the worker node to join the KubeEdge cluster, which is running on the CloudCore node. Now on the CloudCore node, you can run this kubecontrol get nodes command to check for the KubeEdge cluster installation. We're showing here we already have a kind control plane node which is already ready on the master node, which indicate that our KubeEdge cluster has been installed correctly. If you can run docker ps-a command, it's going to show you that this KubeEdge cluster is running on the kindest node on the master node. In a little while, on both of the worker nodes, you can see that KubeEdge has been installed correctly, and then you're ready to join the work nodes to the KubeEdge cluster running on the Cloud Core node. From the worker node, go to /root directory and then run bash the path of the shell script, and the name of the shell script will be edge core join.shell. And you're following this bash command, you will add the IP of the Cloud Core node, the token that you copied from the Cloud Core node, and then the name that you specify for each of the worker nodes. So you can use edge 1 for the first worker node and edge 2 for the second worker node, or any other name that you would like to have. The KubeEdge running on the worker node will give you some output indicating that it's communicating with the Cloud Core node, and at the end of the output it's saying KubeEdge edge core is running and it has been successfully set up in the cluster. And then go back to the Cloud Core node, you can run kubecontrol get nodes to check the status of the worker nodes in the cluster. It will take a little bit while for them to get ready, and then at the end you can see that all the nodes in the cluster, including the Cloud Core node, both of the worker nodes, are ready, and you're ready to deploy your applications in the KubeEdge cluster. Task 2, KubeEdge counter demo application. In this chapter, we're going to set up a KubeEdge example application, which is a counter demo. In this application, we're going to create two components. One is the counter control application running on the Cloud Core node, and then the counter application running on one of the worker nodes. So the first step is to clone a GitHub repository from KubeEdge into your KubeEdge installation folders on your Cloud Core node. Once this is done, go to that folder that has your KubeEdge counter demo application, and then use the seed command to change the name of the node to the one that you're going to deploy this application on. Then use the kubecontrol create command with the name of the YAML file to deploy the resources in your cluster. First, you will create the model of the device using the KubeEdge counter model.yaml file, and then you will create the actual counter device using the counter instance.yaml. Once you create the device model and then the actual device, you will need to build the Docker containers for both the front-end web controller and the counter running on the edge node. First, find the folder that is named web controller app, and then build the Docker container for the web controller running on the master node. After the Docker container is built, go to the CRD folder and run the web controller running on the master node. Now switch to the counter mapper folder and build the Docker container for the counter application running on the edge node. Once the container is built, go to the CRDs folder and run the counter application on the edge node by running kubecontrol create -f kubeedge pycounter app.yaml. You can see that the counter application has been created on the edge node. Now you can run a kubecontrol get pods command to check for the pods that have been deployed on both the Cloud Core node and the Edge Core nodes. You can see that both applications are running on the nodes. Now you can switch to a web browser and connect to the public IP of your AWS EC2 instance to connect to your web controller application running on the Cloud Core node. You can see the web controller application running on the Cloud Core node has a very simple web page that allows you to execute some commands, for example, on and off, and check the status of your counter application. From the web page here, we can select an action, in this case on, and then click execute to execute turn on counter action on the Edge node. Switch back to the command line and go to the Edge node terminal and run a docker ps-a command to show the Docker containers that is running on the Edge core node, which is running the counter application. Once you find the Docker containers running on the Edge core node, copy the ID of the Docker container and run docker logs-f, the ID of the container, to see the running counter application on the Edge node. From the output here, we can see that this counter application is running a counter that outputs a number after every second. Go back to the web page. You can select a different action on the Edge node. For example, check the status of the running counter application, and it's going to show you what's the status of the counter on the Edge node. Another way to check the status of the counter application is going back to the Cloud Core node and run kubecontrol get device counter -o YAML -w command. The output will show you the information of all the device and the application that are running on both of the core nodes, as well as the value of the number from the counter application running on the Edge core node. You can see that the value from the output on the Cloud Core node is synchronized with the number that are showing on the Edge core node, and it's updating after every second. Now you can go back to the web page and click off to turn off the counter. You can see from the output on the Edge core node that the counter application has been stopped. You can still go back to the web page and then turn on the counter again, and it'll restart over. Okay, that's it for the counter demo application, and we'll go to the next task. Task 3, Edge Computing with the Bioinformatics application. Go to your command line and switch to the terminal on the Cloud Core node. From the Cloud Core node, you will switch to the root user and go to the root KubeEdge demo folder that you have previously downloaded from our Git repo. From here, check the contents of a YAML file called fastqc deployment. This YAML file will configure the Docker container that will be running on the Edge core node that runs a bioinformatics application. Using your favorite text editor such as Vim or Nano, and modify this fastqc deployment.yaml file. From within the file, change the Kubernetes IO/hostname from name of your node to the actual name of the node that you're going to deploy this bioinformatics application. Since we're running two nodes in the Edge course, one large and one micro, you can change this value to either of your nodes in your cluster. So in our case, we're changing the name of the Edge core node to Edge Small, which is running a t2.micro instance in the AWS account. After you modify the value, exit the text editor and use the cat command to check the contents of the file to make sure that the hostname has been modified. From the same directory, run kubecontrol apply -f fastqc deployment YAML to create the bioinformatics application on the Edge core node. Once you create the deployment, you can run kubectl get deployment command to check the status of the deployment. You can see that a deployment named fastqc has been deployed but is not ready yet. If you run a kubectl get pod command, you can see that a pod is currently being created with the status of container creating. This container creating process will take a few minutes because the Docker container for the fastqc bioinformatics application is quite large, and it will take a few minutes to download the Docker image from our Docker Hub repository. Meanwhile, you can run the kubectl describe pod with the ID of the pod to see the detailed information on the deployment of this pod on the Edge core node. After a few minutes, if you run the kubectl get pod again, you can see that the pod has finally been deployed and is currently in a running status. At this stage, we can switch to the terminal on the Edge core node, switch to the root user, and run docker ps-a to check for the Docker container running on the Edge core node for the bioinformatics application. We can see that the first Docker container showing on the output on your screen is the Docker container running the bioinformatics application on the Edge core node. Now you can copy the ID of the Docker container and run docker logs the ID to check for the log of the bioinformatics application running inside the container. The output of the Docker logs will show you the step-by-step running process of the bioinformatics application, as well as some commands to check for the status of the workflow inside the Docker container. We have created a bash shell script to help you to check the status of your workflow running on the Edge core node. From the same directory, run bash./check-status.shell with the ID of your Docker container, and the output from this command will show you the status of your running workflow by showing the percentage of the jobs that have been done from the workflow. If your workflow has not yet been finished, it's going to ask you to wait for a little bit for the job to finish. Just keep checking with the same command, and when the workflow is done, it's going to show you all the output with the statistics of the workflow running on your Edge core node. The most important information from the output is the workflow wall time of the workflow that has been done. So here on this Edge core node, we're showing that the workflow was done in 2 minutes and 4 seconds. Feel free to explore around with the datasets and then the other information from the workflow. This is the end of the demo, and next we'll leave an assignment to you to repeat this process by running this bioinformatics workflow on a different Edge core node. In this case, we'll ask you to run your workflow on the t2.large instance in your AWS account. After you run the workflow on the large instance, please check the wall time on the large instance and compare it with the small instance that we just did. Can you observe any difference?